My name is Brendan Alvey, and I'll be giving this talk on improving explosive hazard detection with simulated and augmented data for an unmanned aerial system. From the University of Missouri, we have myself, Derek Anderson, James Keller, Andrew Buck, Grant Scott, and Dominic Ho. From the U.S. Army, we have Claire Yang and Brad Libby, who all collaborated on this paper. I'm going to skip the outline and go straight into the introduction here. Okay, so above ground explosive hazard detection is a problem that is probably better suited for drones than humans. The drones, they're replaceable if we don't want humans to get too near explosive hazards if we can help it. Previously, there's been a handheld project, and now we can kind of use drones to try to detect explosive hazards. And the problem of detecting explosive hazards is really a pretty difficult one. The targets can vary in size and shape and composition. There's a large variety of environments, and they have different features. There's some that are grassy, some that are rocky, some that have gravel, all kinds of different roads or people or buildings. There's all sorts of things that can change how the emplacements look in their context. Now, the individual emplacements can also vary a lot. We can have targets that imagine a disc, right? Which when it's flat, it looks like a circle. If it's sort of turned on its side, then from above, it could look like just a line, right? And the time of day can really change the shadows. So if we're looking at images that were collected in the morning or the evening, we might have really long shadows where the targets have, where targets that are thin might actually have very long shadows, right? But if we're looking at high noon, then those targets could almost totally disappear. And what we've done is we've used the Unreal Engine here, and we've generated and expanded our training and validation sets by using totally simulated imagery of explosive hazards. And then we've also taken simulated target templates that we've made in Unreal Engine, and we've used those to create more data from the existing real data that we already had. And the idea with both of those is to build better detection models by including that extra data. What this slide is showing is some images generated from the Unreal Engine. And with the latest version of Unreal Engine, you can enable ray tracing, which allows for some really great realistic shadows and reflections that are happening in totally in real time. We have this really nice editor that lets us move objects around and rotate them and change their scale very easily. And then all these models shown in these pictures are ones that were free or available through this TurboSquid program, which is a really nice website that we've been going to. On this slide, we show that we've got a custom stencil buffer that Unreal Engine lets us make, which allows us to create these ground truths and target templates that are really useful for us. So since we're only processing grayscale imagery, we can make a grayscale ground truth template by outputting the red and green as grayscale and the blue as this object ID. So to generate simulated data, what we do is we first start with a target and an environment, and then we randomly put the targets in different places with different scale. So that's what this first image on the top left is showing. And then what we can do is we can create a simulated flight pattern with all kinds of different viewing angles that is supposed to kind of mimic a drone. And then instead of just using one background, what we can do is we can put those same emplacements and some of the environment features and put them on totally different backgrounds and change and that way we can have the target seen with all these different background features and emplacements. And then what we can do is we can also vary the sun and the shadow, and that will change the shadow position. So in the Unreal Engine, we can just move the sun around and we get totally different shadows and totally different lighting effects. What this slide is showing is some of the images that we've actually generated from simulation in Unreal Engine. And so these are totally simulated images. We've created the explosive hazard templates, and we've put them in environments, and then we've rendered them in grayscale with some of these camera variations that look more like real images collected from drones. So all of these are just totally generated with Unreal Engine. Now the next thing that we did is we've taken something that we call altitude, or we've created something that we call altitude modulated augmentation. So what we do is we take an image, and since it was collected on these are real images collected on a drone, and each one of those has a corresponding altitude, and we can use that altitude to then insert target templates, which we've created totally in simulation in Unreal Engine, and we can insert them at the right scale so that they look correct when they're placed in these images. And then what we can do is we can add some variations to both the target templates and to the images themselves, those background images, and we can add a lot of variation. We call them sort of augmentations in order to expand the data sets to have more variation and to make our models more robust. So what this slide is showing is the target templates that we used for AMA. So on the top we have these false color images, the grayscale object ID, and we've got shadow information, which you can see on the bottom with we're able to extract. So you can see these checkerboard patterns, which are just showing that's pretty much a totally transparent area. Then we have the target templates grayscale image, and then we have these shadows, which we can then use to darken the background once we insert these target templates. On this slide, we have real images, or real background images rather, without any real targets in them. We have all the targets that are inserted in these images are simulated target templates. They're templates that were generated in Unreal Engine, and then we have inserted them into these real images with different rotations and with noise added and with different scales and some compression effects, all these different effects, these variations that we hope that by including them in our data set will make our model just detect these objects rather than tune to any sort of context in the background or the specific placements or the specific kind of color of the images, or not color, but the presentation in grayscale. Okay, so then for the experiment, what we did is we have this data set which consists of 10 runs of explosive hazards. The hazards came in 4 varieties. We have the first variety, which is a flat circular object. It's sort of like a disc that's a few inches thick. We have, and for the second target, we have a larger version of that first target. Then for the third target, we have a cylinder, which has some flat metal feet. It has these 6 kind of flat metal feet that are equally spaced. And then for target 4, we have a rectangular kind of concave object. And if we go back just a couple slides here to these templates, you can kind of get an idea of what these targets looked like. We have on the left the one with the metal feet. We have this concave object in the middle, and on the right is that circular object, which we have kind of like 2 varieties of sizes of. So these images were collected from a drone flying over explosive hazards. They were looking only nadir, so straight down, and they're collected over a range of altitudes, but within a relatively limited range that's we won't disclose, but it's not too high up. So each images has a corresponding altitude, like I said, that they were captured at, and so we can use those to then generate synthetic images with, or AMA images that we'll refer to. And like I said, these images were all grayscale, and their resolution was actually relatively small. It was 640 by 512. And what this is showing, this kind of table here, is just all the different, the number of labels for each of the different target types. And so you'll see one thing to note is that target 3 is not represented here in testing run 1. So later, testing run 1. So later when we show the rock curves for these, This one will not have any ground truth points. And also, it's important to note, I think, that there's no training images of target 4 in the real data here, right? So we would expect a model trained only on real data to do pretty poorly on target 4. In this slide, we're going to show the results of training YOLO v5 models using all of these different images that we've been talking about. So on the left, we've trained a model that we'll call the control on just original images that are actually collected from a real drone flying over explosive hazards. And like we kind of mentioned here on target 4 or on target type 4, it hasn't trained on any examples of this. So really any of these detections are nothing to write home about. This is probably at a low enough confidence that most of these are letting in false alarms, and this wouldn't really be a model that I think you would want to use. On the right, though, we have the results of a model that's been trained on 720 simulated images. So these are images that were totally simulated of explosive hazards. And we can see that for target type 1, we're actually doing pretty well here for this run 2. We're detecting 80% of them with a reasonable, or with letting in some false alarms. And we're pretty happy with starting to get some improvement here, and because this was really just a first shot at trying to simulate explosive hazards. On the right hand side, we're not seeing, or on target type 2 rather, we're not seeing too much of improvement. We are seeing a bit over the control. For target type 3, really happy to see that on run 2 we're getting 100% PD for this target type. And then for target type 4, we're still seeing not the best performance, but we're starting to see some improvement over the control. So that's encouraging. Now on this slide, what we're showing on the right hand side is, well, on the left hand side we've left it the same. On the right hand side, what we've done is we've trained 1,750 AMA generated images. And so these are images that were taken from, they were real images from the drone, but they were just background images with no targets. And then we've inserted randomly all these target templates into them. And then we've trained a model, or we've trained models on them. And I should note, actually, before I go further, is that with each of these graphs, what we're showing here is the top curve is going to be, or for each parameters, or each training set, we have trained 10 models, 10 YOLO models. And so the top dotted curves are going to be the maximum that any of the models does. The bottom dotted curve is going to be the minimum that those 10 models do, and the bold line is going to be the average. So on the right hand side, we have the AMA generated models results, and now we're really starting to see some models that we think are ones that we might really want to use. We've got for target type 1, we're starting seeing runs 1 and 2, which are the runs that we are pretty much concerned about. We're not really too concerned with run 0. We're seeing those do really well. And then on target type 2, we're also starting to see that we're really starting to do pretty well on there. Target type 3, we've seen a slight drop over the simulated, but we're starting to do even some of the detections in run 0. And on type 4 here, we have really great improvement here on run 1 for this target type. And then finally, what we've done is we've trained a model that combines all 3 of these data sets. So sort of the control, the AMA, and the simulated, each one of those was trained independently in what I've shown in the previous graphs. Then what we've done is we've taken all 3 of those and put them together into one model. And as you might expect, this one does the best. We have on the right the results, and I'll just let them kind of speak for themselves, but we're doing pretty well for most of them. We still have some trouble on that red run, but we sort of expect so, as most of those targets are occluded. Okay, so then some future work for this is that, well, we could develop more realistic shadows for AMA. If we look back at the images, you can see that they're not necessarily generated in a way that's consistent with the time of day or the angle of the sun. And the shadows in the whole scene should probably be consistent in order to build a neural net that is actually learning realistic representations of data. And we could also create more background environments in simulation. We've only really shown a few, but there's probably if we trained over a large variety, that would probably make the models more robust. We can also investigate misdetections and mimic scenarios in AMA and or simulation. So we can look at the detections that were that we really should have gotten, but we just didn't, and see what we can do to try to include more, or what kind of data we think we should include in AMA or simulation in order to improve those models. And then what we can also do is we can add more clutter and confusers and sort of obfuscate the targets to try to build models that are robust to those types of those types of things. And then we can also use this altitude information to possibly filter alarms based on the bounding boxes. So, when we're flying over, we probably only expect certain targets to be of a certain size. And if we see maybe a very large declaration, but we're very high up, then we probably don't think that it's right. And then we can also segment these images to try to intelligently insert or obfuscate simulated targets. What I mean by that is, if we see a tree, we probably don't want to insert a target on top of a tree, but we might want to insert it on the edge of a tree and somehow come up with a method to partially occlude it. That could be a really smart way to try to come up with images that are sort of on these edge cases that are hard to get. And so with that, I'm just going to leave this slide up with the acknowledgement and then say thank you. And that is all I have for you.